Hello and thank you everyone for making the time to join our series webinars. Today we're going to cover a new subject in our series webinar. We're going to be talking about Electro-Thermo-Mechanical simulation of eddy current braking system in EMS as an add-in to SOLIDWORKS. As you know, EMS is a full 3D that sits right inside SOLIDWORKS, and we're going to show you the electrothermal part of that and the challenges when it comes to doing such an application. My name is Adam Kibir. I'm the sales manager, and it's going to be online today with me today my colleague Majdi Fala, who is an application engineer. So hopefully with our joint effort, we're going to give you the best information needed, and we'll enjoy this meeting together, and you guys come up with plenty of useful information that can help you build better career and do better jobs. Before we start on this, please use the chat window to send in any questions as you see in the screen. Of course, the instructor, Majdi, will be able to answer them after the webinar is finished. Also, a webinar of the recording link will be sent to all the attendees and registrants. The agenda of our today's webinar, we're going to be speaking, or it's going to unfold as follows. First, we're going to do a company overview, locations, product licensing. Then we'll do the actual presentation. Then speak about our products and applications we cover. Plus, share with you the learning resources available for offline, situations like talking to each other or not through webinar, and how to submit all types of requests. Again, welcome, and let's get going on this. So our company was founded, or EMWorks Inc., Electromagnetic Works Inc., there is no difference. Our company was founded in the year 2000 with the different office locations. We are headquartered in Montreal, Canada, but we do have two other main offices, one in Japan, the other one in Germany. We also have, an extensive network of sales where there's presentation of us in other parts of the country. So apart from Japan and Germany and Canada, we work through the rest of the world, with our SOLIDWORKS resellers or SOLIDWORKS VARs. Most of them, about 90% of them, are able to provide support for our products. Of course, in one of the main areas is where we have a heavy presence is in the United States of America. Indeed, we do have a strong, R&D, department with very highly qualified engineers. The lowest of them will have a master's degree in some sort of either physical or physics or magnetics or computer development. As far as our products, they go as follows. So overall, we cover all types of currency or frequency ranges, from DC up to the light, frequency. And to cover all that area, we put in the market different products. The main product, and it's going to be the subject of our presentation today, is EMS. That's number one, and it's a full 3D FEA that is built inside SOLIDWORKS for all types of applications. One of them is the eddy current braking, which is today's demo again, or webinar again. The second one, once you move from the DC level to the megahertz level, you start going gigahertz. You're talking about the RF and microwave frequency, and where you can analyze antennas and so on. And for that, to solve it, we provide the product HFWorks for that. HFWorks is also a full 3D solution. Now, in between both of these products, we offer what is called EMWorks 2D, which basically it's built inside SOLIDWORKS, but it's only 2D, which is a very powerful, really accurate tool, in addition to motor wizard, wherein it's a template-based solution for solving all types of models. Motors. All you have to do is enter the parameters in the template, and the software will do the rest for you. The MWorks 2D, on the other hand, is for applications where 3D is not needed, for the sake of time savings, for capital or money and savings, precious savings. MWorks 2D could be also a good way to go with us. So with all these combined together, we pretty much have, we try to offer a multi-physics solution all within the SOLIDWORKS environment. Now it's time to pass the screen to my colleague Majdi to do the technical presentation. I hope you enjoy it. And after that, I will reconnect again to share with you the licensing types we offer and how you can get hold of us and how you can better, evaluate and understand our solution. Here you go, Majdi. The screen is yours.
Thank you, Adam. Hello, dear attendees, and thank you all for taking time and joining us in today's webinar. I am Majdi, Senior Application Engineer at EMWorks, and I will provide the technical part of this demonstration. In this session, we will cover the topic of eddy current brakes systems and see how we can use EMS for SolidWorks to perform electro-thermo-mechanical simulations for such application. Before we start, let's have a look on our agenda for today. In today's presentation, we are going to start by a memory refresh about eddy current braking principle. Then we will see what are the main design challenges posed by this application. Later on, we will focus on some simulations of a couple of eddy current brakes solved using EMS. Also, we'll have a live demonstration of EMS, and at the end we will finish our presentation with a conclusion about what we have seen. Unlike mechanical brakes, which are based on friction and kinematic energy, eddy current brakes rely on electromagnetics to stop objects from moving. Ideally, a non-ferromagnetic conductive disk rotates perpendicularly through constant magnetic field. As the disk rotates, it induces eddy currents. According to Land's law, these currents will produce an opposite response to the initial magnetic field. Hence, these forces created by this response create a motion in opposite direction to the original motion. This phenomenon is used in what's called eddy current brakes, which is a contactless braking system. We can have both linear and rotary eddy current brakes, and they can be found in several fields and applications like transportation, in buses, cars and trains, and in amusement park rides like roller coaster and many other applications. We can find several types of eddy current brakes, and this is depending on their construction, like axial or rotary braking, and also depending on their excitation. So they can be made of permanent magnets or electromagnets, or a combination of both of them, which is called hybrid brake. So at the earliest stages, analytical solutions were used to estimate and predict the different parameters of these systems before going to lab and doing prototypes and testing. But this approach is no longer practical because it doesn't provide an accurate solution, since it needs usually some approximation and it doesn't answer all the issues posed by such application. So what are the main challenges that we can face while designing an eddy current brakes? Here we can see the main issues that we need to address if we want to build our eddy current brake. The main quantity we must calculate is the braking torque generated by the induced eddy currents. We should be able to compute the torque for different eddy brakes, geometry, and versus all the possible variables like speed, excitation, number of poles, air gaps, and so on. We need to study the dynamic response of our system to find out the braking time as well. In the eddy braking system, the mechanical energy is converted into ohmic losses dissipated in the moving parts. This power has to be estimated and as well as the generated heat caused by these losses. Overall, these are the main quantities a designer has to evaluate before creating a prototype of an eddy current braking system. EMS for SolidWorks, which is an electromagnetic solution, as my colleague Adam introduced earlier, is proposed to help you solving these issues. We should not also forget the geometrical issue of this problem. So SolidWorks, where EMS is integrated, is a flexible CAD tool that allows you to make your innovative ideas into real models ready for simulation and later for manufacturing. So let's discover this platform of EMS and SolidWorks. In this slide, we can see our first example, which is a passive axial eddy current brake. It contains two fixed stator parts made of permanent magnets and the back iron. The magnets that belong to the same stator side, they have the same magnetization direction. A rotating copper disc is located at the middle of these parts with an air gap of 0.5 millimeter. An additional cylindrical part made of iron is added to conduct the flux between both sides of the stator. Now let's quickly have a look inside or in EMS inside SolidWorks and how we can set up such a problem to get the braking torque and other parameters of such application. So now we are inside SolidWorks. This is our simulated or our studied eddy current braking system. It's made, as we mentioned, it's made of some back iron and lateral iron parts, and at the middle we can find the rotating copper disc, and also we have the magnetic poles. So as we said, EMS is fully integrated inside SolidWorks. So let's go to EMS tab. This is EMS 3. It has the same look and feel as SolidWorks. So let's try to create a new study. Okay, this is a new study. So we have, as shown here, we have 6 modules. So EMS comes with 6 modules, 3 for magnetic simulations, so like magnetostatic, AC, and transient, and 3 for electric simulations. So we have electrostatic, electric conduction, and AC electric. So we have also the option of parameterization, so we can parameterize whether geometrical or simulation variables. Let's see now the coupling options. So EMS comes with a few multiphysics options like thermal, structural, linear, static, and motion and circuit coupling. So, or we can also perform a combination of them. So we can have like thermal plus structural, motion plus thermal, and so on. So this is mainly the multiphysics options of EMS. So let's try to create a new study here. Okay, transient magnetic. So for this kind of simulation, we need transient magnetic simulation. It's time domain simulation. So, and later we will add the motion or add the SolidWorks motion coupling. Now let's just create a new study. So whether you start by creating your motion, your SolidWorks motion study, or you create your transient magnetic study, then couple this study to SolidWorks motion after you create the motion. So this is a new study. A new study is created now. So we have at the first or at the top level, we have the material list. So we have the material here. So let's try to apply material. So we can use this right click and click on apply material. So this is EMS material library. It is a rich and well organized material library. So it also the user has the possibility to modify, edit, or import his own data to this material. So he can import, for example, create new materials, import pH curves, temperature depending materials, so he can do whatever he wants using this library. Now let's apply this mild steel. So, and repeat the steps. So we can repeat the steps to apply the material for the rest of components. So we can do this. So I have already defined materials. Let's try to copy my already defined study from my already defined study, paste. So I pasted this. So this, as you can see, this is the magnetic poles, the permanent magnets. So we have an alternated magnetization. So you can see here it's alternating. So you can apply the coercivity direction using right click. So this is how to apply the magnetization. So you can work with the global system, or you can define your local coordinate system as well. So we have Cartesian, cylindrical, and spherical systems. So use this page to define the magnetization of your magnets. So you can do multi-selection. So you can define, for example, the same magnetization to several magnets, or you can check one by one. That's depends on the setup. So this is mainly what you need to do at the beginning. So later, if you have coils, so you can create a new coil. So we have two options, solid and wound coil. So you can, for example, choose this option, wound coil. So you select the entity, your coil, entry and exit ports. So you sometimes you have both entry and exit ports are the same. So you check this option. So we have general properties here, where you can define the number of turns, the diameter, the wire diameter, choose whether it is current or voltage driven coil. So, and here the source. So you have several options. You have DC, you have sinusoidal, you can import a curve, and so on. So you can define your excitation depending on your settings. This is ideally what you need to do with the coils. So later we have forces and torques. So you can define, so where if you want to compute a force or a torque, use this option. So you can define vertical work or Lorentz force. So vertical work is used mainly when we have, or when we want to compute the force or the torque in ferromagnetic parts, while the Lorentz force is used for non-ferromagnetic parts with current. So like when we want to compute the force in coils, or in this copper disc. This copper disc is non-ferromagnetic part and it has a current. And at the bottom we have this option, or the mesh section. You can create the mesh. So just by default you can use the default settings. So we have some options here. You can apply mesh control. So you can specify your the mesh element in specific regions and specific bodies or surfaces. And also we have the option of, let's see it again, we have the option of automatic adaptation meshing. So this is the meshing. So we have manual meshing and we have adaptive meshing. So you can use this to get accurate results without taking into account, or without defining your own settings for the mesh. So you can use the adaptation option to get the accurate results. So you can use the adaptation option as well to get accurate results. So you can use the adaptive option to get more accurate results. So this is overall about the mesh. So now let's have a look on the motion study. So let's check, for example, let's check motion study 1. So for the simulation, or the steady state simulation, so let's suppose that we will run our disk with a constant speed. So we go inside to compute the braking torque. So at steady state, so we create a new motion study. We define a rotary motor. So let's try to create a new motion study. This is a new motion study. So we have animation, basic motion. We choose motion analysis. We select this option. rotary motor and select this phase. So we have this option. So our motor will rotate in negative direction. So better we have positive direction. So let's specify. So no. So our generated torque will be negative in this case because we have a positive motion, and we know according to Land's law that the torque generated will be opposite, will have an opposite response. Okay, so we define the value of the speed. So like 1000 rpm, we can use this constant speed, or we define the speed using data points. So we can use this option to define the speed. So we have displacement, linear, and for example, we want to run the simulation with 1000 rpm. It's 6000 degree per second. So this is the speed, as you can see, our speed. So after that, we define the simulation time. So this kind of problem, it reaches the steady state in maybe a few milliseconds. So like 20 millisecond. So here is our end time, and then let's define the number of frames per second. So let's put, for example, 1000. So 1000 times 20 millisecond gives 20 steps. So our simulation will run 20 time steps. Okay, this is basically what you need to do to have or to get the braking torque at steady state. This is what we need to do. This is a motor-driven motion. It's called a motor-driven motion. So now let's see if we wanna compute or check the deceleration phase. If we wanna compute the braking torque, the dynamic behavior of the braking phase. Okay, so this is, we need to create another motion study. So we define here EMS will compute the torque. So based on an initial velocity, we should define an initial velocity. So our disk has an initial velocity. This is the initial velocity. Let's put this initial velocity in positive reverse direction. So based on this velocity, EMS will compute the torque and send it to SOLIDWORKS Motion. So let's now define the link between EMS and SOLIDWORKS Motion, which is the torque. Here is the torque. So make sure that the torque is in positive direction, always in positive direction. So let's add this edge. So now we have positive torque. Keep this 0 because this value will be computed by EMS and sent to SOLIDWORKS Motion. Okay, this torque is computed. This is the electromagnetic torque computed by EMS. Oh, now let's do the same. We define, for example, some end time, like 50 milliseconds, and put the number of frames. So these are random values. Okay, these are some random values. So now our disk is rotating. Later on, when we do the coupling and solve the problem, we will get the real behavior, the dynamic behavior. Once the braking torque is created, this disk will be stopped. It will be stopped after a certain time. So this is overall what we need to do for this kind of problem. So we have to create a transient magnetic simulation, then create whether if we want to do steady state simulation, we just create a motion with a constant speed motor, or if we want to study the dynamic behavior of our system, we can apply initial velocity and apply a torque that will be computed by the software, by EMS. So this is basically two types of simulation that you need to do for eddy current braking systems. So now let's get back to our simulation again, our presentation, sorry, again. Now back to our presentation, we can see in this slide a couple of results plots. At the left we have the magnetic field as a fringe and vector plots. They show how the field is circulating through the back and lateral iron parts. So we have two closed loops. This is like one or first closed loop. This is another closed loop. Each loop is or contains two magnetic poles. The right side we can see the magnetic field in the disk. We can note 10 small loops. Each loop is located between two magnetic poles of the stator parts. The rotation of the copper disk inside the magnetic field created between both stator sides generates an induced eddy current in the disk. These currents, as can be seen, are maximum between the magnetic poles as well. So as you can see here, these are the maximum eddy currents generated in the disk, and they are located between the magnetic poles. Here is a vector plot. We can see the loops here, and this plot is a streamline plot created by EMS. It shows some continuous lines of the induced eddy currents. Those eddy currents act in an opposite way as we explained at the beginning. So as a result, the generated torque, more precisely the braking torque, is in opposite direction to the motion. It tends to stop the rotation of the disk. This torque depends on several factors like the speed. In the left figure we can see the variation of the torque versus the rotation speed. It shows that the torque increases with the speed. As you can see here, the torque increases with the speed. A slight difference between the simulated and the experimental results can be noticed at the speed of 1800 rpm here, and this is due to the temperature effect, which is not taken into account in this simulation. The dissipated power as well, this is the dissipated power as well, is increasing with the speed. This is the dissipated power inside the copper disk. Now we changed the magnetization of the poles. We have an alternating magnetization. Now, as you can see here, this is an alternating magnetization. So we have north-south poles. We are investigating now how this can change, or this change can impact the braking torque. Since the magnets now are alternated, we don't need anymore that cylindrical iron part to close the magnetic field path. We have now one magnetic loop from one to another pole of the same stator side, then through the air gap and the copper to the second stator side. This helps to increase the field going through the copper disk and reduce the used steel to make our system lighter. As you can see here, some loops. Here is loop from one stator side to another stator side. The loop is now shorter, and the maximum field is going through the copper disk. So here are different plots of the induced eddy currents results. So this is an animation of the induced eddy currents. The disk is rotating and the eddy currents are generated in the disk. So we were able in the previous slides to see 3D results of the magnetic fields. Now using EMS 2D plots, we can obtain plots of the magnetic results in points or along a line or an arc, along an arc. You can directly select points from your model or import defined points from SOLIDWORKS. So this graph shows the variation of the magnetic field and the induced currents density results in the copper disk. The high spots of the results are in the small loops we saw in the 3D results area. So these are the high spots of both magnetic field and induced eddy currents, and they are located in the high between the magnetic poles in these loops we saw. So as can be seen from the right figure, the new magnets arrangement helped to improve the braking torque of our system. So at the end we got a higher torque or a braking torque by using this magnet arrangement. So as you can see, the torque now can reach values around 60 millinewton meter. So, and the previous one was about, the maximum torque was about 30 millinewton meter. This is the dissipated power also increased with the speed and with the new magnet arrangement. So this is one side of the problem. So we were able to solve this problem, and we got higher torque with a new arrangement. We can do another arrangement, magnet arrangement, and we can get higher torque than this. In addition to the magnetization arrangement, EMS is used now to investigate the impact of other factors on the braking torque. In the left side, we can see that the braking torque decreased when we removed the top and the bottom back iron of the stator. So here, for example, we removed the back and the back iron parts, so we got lower torque. At the right side, ran the simulation for 3 different magnets and got these results. So as you can see, the neodymium magnet N42 gives the highest torque compared to ceramic and cobalt magnets. And this is normal because the neodymium magnet has the highest magnetic resonance compared to these magnets. So despite this, neodymium magnets are known by their great resonance. They are expensive and heavy. So sometimes, and when it is possible, we may use additional ceramic magnets to avoid the use of neodymium magnets. So if we have space, we can insert more ceramic or cobalt magnets to avoid the use of neodymium or the expensive and heavy neodymium magnets. So after covering the steady state response of the studied eddy current brake and the previous slides, now we move to have a look on the dynamic or transient response of this application. This simulation type helps to better predict the real-life behavior of our system. It allows to compute the braking time or deceleration phase of the brake. As we mentioned earlier in the live demonstration, we use a torque-driven motion and we apply an initial angular velocity to the rotating disc. Using the torque calculated by EMS, SOLIDWORKS Motion computes the mechanical parameters like the position and the speed. So we can see in the left side the dynamic torque versus different speed rates. The torque starts to increase from 0 when the brake is activated. It reaches a peak value. Then it decreases until it becomes 0 again. The torque decreases because the speed is decreasing as well due to the braking torque. This interaction ends when both of them became close to 0. So as you can see here, these are the braking torque during a deceleration phase. So the torque initially when the braking system is off is 0. Then when it is activated, it starts to increase. Then it reaches a peak value. For example, this is the peak value for the speed 1200 RPMs. Then it decreases when the rotation of the disc becomes or is decreasing. So as well. So until both here, as you can see, it becomes 0. And from the right figure, it can be confirmed that for the 3 simulated initial speeds, the braking time is almost the same, which is around 20 milliseconds. Now we end with the previous example, or the first example. Now we have a second example, which is an active eddy current braking system with or is made of electromagnet instead of the permanent magnet. Such system gives more flexibility since we can adjust the current to vary the produced braking torque. The braking torque of this system this system versus speed is shown in the top right side. It is between 8 and 12 Newton meter. So as you can see, this is the braking torque of this system for some speed, and it is increasing. Then it reaches some peak value here around 400 RPM. Then it decreased. This is the braking torque of this system with one electromagnet. At the bottom right side, we have the braking torque results versus the applied current. As you can see, the torque increases with the applied current. So once we increase the current, we get higher torque in our system, in our braking system. So we saw how the current can affect the braking torque, but now what if we change the number of poles? And another question that EMS can help to answer. Using SolidWorks pattern feature, we can easily vary the number of poles. So at the previous simulation, we had one pole. Here we have two poles. So we only use that feature of SolidWorks, the pattern, so we circular pattern, so we can duplicate our initial pole. So now we have two poles, and here we have four poles. Braking torque is shown versus the number of poles. It also increases when we add more poles. So it can be notes that the braking torque increases with the number of poles. As you can see, it's linear, it has a linear behavior, and it increases with the number of poles. So this helps to avoid the steel saturation and the heating of the coil in case we wanted to increase the torque through the current. So adding more poles helps to avoid the steel saturation. If we wanna increase the current with one pole to get higher torque, then we may result in some saturation of the steel and heating the coil because of the current, the high current injected. So till this point, we went through permanent magnet and electromagnet brakes. Now we have a third example, which is made of a combination of them. It's a hybrid excitation. It is a hybrid excitation eddy current brakes. Through this combination, we can have a light and compact structure and ensure some control of the produced braking torque. So we have a combination of a permanent magnet and electromagnet braking system. So as you can see, these are the coils. These are the electromagnets, and here some additional permanent magnets. So the generated eddy current on the copper ring are plotted in the figure of this slide. These are the generated eddy currents of the rotating copper ring. So four big loops can be seen due to the four poles of the stator. We have four poles, so we have four loops as in the first example. So another scenario that can come to our mind, what if we deactivate the magnets? What is the difference in terms of power and braking torque? So let's try to answer these questions. First, we need to switch the magnets into steel. We change the material of the magnet into steel. So we have some cross-section views of the magnetic field that show the main difference. So the top left figure shows the magnetic field of the original model, while the bottom left figure contains the field plot of the model without magnets. The field of the original model is higher when we become close to the air gap, which is the most important region. This can explain why we get higher dissipated power and braking torque in case we have the permanent magnets in our model. So as you can see, this is the bottom figure. The field here is higher, the magnetic field higher, close to the air gap and close to the rotating copper disc. And this is the model without permanent magnets. There is a slight lower magnetic field. This is the green, so it's around 1 Tesla, and here it's maybe around 1.3 Tesla. So the deceleration phase are studied in both cases. So we are studying now the deceleration phase for both cases, without permanent magnets. So we can observe that with permanent magnets, the braking system takes less time to stop the rotating ring. I mean, this is the deceleration torque. This is the braking time and the braking torque of this system during the deceleration phase. So we can see that this orange curve, it shows that the system with permanent magnets can stop the rotating ring in less time. It's around 40 milliseconds or 0.4 second, while for the model without PMs, it takes around 6 or 0.6 a second. Here is the speed behavior of both in both situations. So we have this curve. It shows that the speed reached this 0 in less time, in 0.5 seconds. We come now to our last example. In this example, we are going to see how EMS can help to predict the temperature and the heat generated by the induced losses due to the eddy currents inside the moving parts. This is an important step in the eddy current breaking design. EMS comes with an integrated thermal solver that can be coupled to both electric and magnetic simulations. In our situation, an Electro-Thermo-Mechanical simulation is performed to compute magnetic, mechanical, and thermal results. So in this case, we will couple our magnetic solution to both SOLIDWORKS Motion to get the mechanical results and the thermal solver to get the temperature variation or the temperature results inside the moving parts. So on this slide, we can observe the losses in both rotating parts, which are around 2 kilowatts. The temperature after 90 seconds is around 84 degrees Celsius in both conductive parts, as shown in the middle and the right figures. So let's have a look quickly inside EMS environment to see how we perform this kind of coupling. So back again to SolidWorks, let's see how we can perform this thermal and motion coupling. So let's create a new study. So we have transient magnetic simulation. So as we mentioned earlier, for this kind of problems, we need transient magnetic simulation. Go to coupling. So first, if we want to do, for example, motion coupling only, just check this. Choose to which SolidWorks Motion study we want to couple our magnetic simulation. So let's choose, for example, 3, motion study 3. We select here the moving parts. Here we have this top and bottom disc, and we select the band. The band is a virtual part that is needed to surround only the moving parts. This is something, and it is made of air. So the band is a part that separates moving and fixed parts. This is the band. Later, if we want to add the thermal coupling, so we have two options, whether we have steady state and transient. So you may ask how we can have steady state and we are doing time domain simulation. Yeah, so after finishing the simulation, the transient magnetic simulation coupling to motion, we take the losses, we do the average, and we run a steady state thermal simulation. So we don't rerun again the magnetic simulation. We just solve a steady state thermal simulation. We use the thermal losses or the thermal load as an input for our problem. So after finishing the magnetic simulation, we get the losses, we do like an average of the losses, then we compute the temperature based on that averaged losses. So we have also this option of transient thermal. So we have this option, so we can do in both during the same simulation. So we solve both transient thermal plus transient magnetic simulation. So we do the solving for magnetic and thermal solutions, so both of them at the same time. But for this kind of problem, we only solve for example 20 millisecond, 40 millisecond, maybe 1 second, and this is not a huge time, or this doesn't allow for the thermal simulation to reach the steady state. This is why, for example, if we wanted to reach the steady state, of course, or get some heat, we want always to extend the computation time. So we don't stop with 20 milliseconds, for example, or the electromagnetic simulation time. So this is why, after finishing the magnetic coupled to thermal simulation, we have the option called continue thermal run only. So we continue running the thermal simulation, the transient thermal simulation only. We don't run again the EM solution. So it just based on what we solved from the previous simulation, we continue the thermal simulation only. So let's like here. So if let's suppose that we validate. So I have some studies here. So as you can see, so we have run all or continue thermal run only. So So I got some results, or some magnetic results plus thermal results, but the thermal results is not, I didn't get any heat, so I need to continue the thermal solving. So because my EM solution reached its steady state while the thermal didn't, so just continue thermal run only. It helps to save a lot of time. So this option is really great option to save time. So that's overall what you need to do if you want to use EMS to solve such problems. So this, we have the motion coupling, the thermal coupling. So you can get both dynamic and steady state results of your magnetic simulation. I mean that braking torque in a steady state, or the dynamic behavior of the braking torque. So you can get the braking time. So, and you can couple your magnetic simulation to thermal to get the heat generated in a specific time. So that's all. Let's finish our presentation. So now back to finish our presentation with the conclusion. So as we saw, EMS for SolidWorks was used to study several eddy current breaks. So we performed the simulation of permanent magnet, electromagnet, and hybrid eddy current breaks. So the magnetic fields and the induced eddy currents were calculated. So we got the results of braking torque and the dissipated power versus several scenarios, and we have some compared experimental data. So the braking time, I mean the dynamic behavior of some of the braking system were evaluated. So, and at the end we predicted the heat generated in the conductive part using the mechanical coupling of EMS. So thank you for your patience and attention, and I hand over the screen again to my colleague Adam to continue the presentation. Thank you.
Well, thank you, Majid, for your presentation, and I hope you guys learned enough about how we analyze electromagnetic or eddy current braking inside EMS SolidWorks, and how the two packages work together to provide you with the best solution for your eddy current braking. Now, as far as licensing, and if you care about acquiring a license or knowing more about our license, we offer different types of licenses. We offer commercial licenses. We also offer licenses for academic, for students, instructors, researchers, and all kinds of educational or academic institutions, in addition to a startup program that works well for take by the hand of newly established companies, or companies that are yet to be established and they're on the way to do that. I'm sorry about that. As far as learning resources, what can we put in your hands as a customer? So first of all, EMS, both EMS and HFWorks, all our products come with a section that is called a demo viewer. The demo viewer is a set of pre-set-up examples, so that to shorten the learner curve of using EMS. Use these models that are pre-set up. All you have to do is hit and run, then plot the results. That's one tool. You can also subscribe to one of our channels. That's a lot of info being shared on all the social channels. And we also offer the software also come with the tutorials. On our website, we have plenty of application notes, in addition to a monthly newsletter that we send to our database, and in addition to the blog and paid training. If you want to speed up really the learner curve, paid training will be the way to go. Although I would like to emphasize that if you are good at using SolidWorks, learning one of our products, EMS or HFWorks, won't be difficult at all. So if you want to get hold of us for further needs, be it that you want to get a trial of the software, you want to get a quote, you want some consulting, like how can I do this, what can I do this, would you simulate this for me, give me the results. My situation, my project is one of a kind. What is the best way to go to get the tool so that I do my project and move on without spending a lot of money? And we know some project could be limited as far as the money that is available for magnetic simulation or simulation tools overall. So the best way is to go to our webpage, right here, www.emworks.com, and click on Support tab. And on Support tab, you click on Contact Us. Under the Contact Us, you will have, a template like this, and you select your category, fill in the information, hit Run, hit Submit, and we'll get it. And of course, me or one of my colleagues, since I am the sales manager, will get hold of you and help you further. I would like to mention that the more info you put, especially validating that you're an actual business or an actual institution, that's very important. So we prefer to receive official business emails and official educational mails rather than Gmails and Yahoos of that sort. But of course, you can always get hold of us. We'll reply to you accordingly. That doesn't mean we're not going to help you. We will. Because when you receive a business email, we can simply go on the website and be able to understand more about the customer needs and what they do overall, hence provide a custom solution upon you contacting us. For more details, as I said, EMWorks is the best way to go. But for any particular other questions, you can simply email sales@emworks.com or phone us on the number below. I'm sorry, on the number here, and we'll call you back. We thank you all for your time. I hope you enjoyed it. Stay tuned for more webinars to come with the EMWorks Inc.'s webinar series, be it an EMS, Motor Wizard, EMWorks 2D, HFWorks, Multiphysics, all of that. And rest assured that you do have a solution with us at EMWorks Inc. You all take care now. Bye-bye.